please feel free to ask questions. Let's get the momentum of dialogue going in this meeting, okay? So I'm handing over to you, and welcome.
Okay, thanks, Piers. Thanks for asking me to come to the school and the hospitality of our Brazilian host. And Piers has been planting enough people in the audience to ask questions to the point where, as he said, I don't know if I'll get past the first stage. But I don't care. Let's go at the speed you want, and if I don't finish something, I've given you the reference to an article I wrote some time back, which contains all of this and many more things. So the plan in the beginning is to talk a little bit about the renormalization group. And it's going to have three parts. The first part is what is it? And the second part is why? And the third part is how. So can you read this board here? I can, okay. And easy to see from the back. All right. So I will do those three, then we'll get into particular examples. So renormalization group is a technique you can use to make progress in a class of problems which you can write in terms of a partition function. So if you can formulate your problem as a partition function, then the renormalization group, or RG, has something useful to tell you. So you know that the standard partition function is defined as sum over all the states of this Boltzmann factor. Now sometimes you may have a sum replaced by an integral. So let me just say what I have in mind when I say partition function is some integral and some Boltzmann weight. This d phi is a shorthand for millions of variables you're integrating. And this S is sometimes called action, sometimes called the Boltzmann weight, doesn't matter. It depends on all these millions of variables over which you do the integral. If a problem has that form, then the RG is useful. So let me begin by telling you, or convincing you, that a large class of problems fall under that category. So the first ones are, of course, problems in statistical mechanics, which are already in the form of a big sum or big integral. So it's not important, by the way, it's a sum or integral. The ideas work. Either way, I will be focusing on things that look like integrals. So all of stat mech belongs to this category, and so does all of quantum mechanics. Whereas in quantum mechanics, we're all interested in the time evolution operator. And if you formally continue this from real time to imaginary time, you get this guy, e to the minus beta h, where beta is minus it. And the trace of e to the minus beta h is the partition function for quantum statistical mechanics. So that's a very intimate connection between quantum statistical mechanics and real-time evolution of quantum systems. If you can solve this problem, you're getting the answer to this problem in the complex plane, and you just got to rotate by 90 degrees. So I will not make the distinction, and I will treat all these problems as problems of this type. So let's go to this formulation of the problem and take one simple example. This is the example, Piers, that I will never cross. That's the harmonic oscillator times A dagger A. Suppose this is your problem. So A and A dagger are standard boson operators. They have the standard boson commutation rules. And if you want to take this trace, we can take the trace by using a complete set of harmonic oscillator wave functions. But for our purposes, it's more useful to use a different basis for taking the trace. And they are in terms of these coherent states. Z, which are eigenstates of the lowering operator. And the adjoint of that will be written like Z bar A dagger, Z bar. Now, I won't go into how you can do this. This is pretty standard in quantum mechanics. Now, these states, Z, are a continuous set of states, unlike the oscillator state, which are labeled by an integer n. And the formula of resolving identity looks like this. There are some factors of 2 pi. I'm just not going to write them. There are some 2 pi's in this, but I don't even want to begin what is a failed process. So I will write all these things without the factors. If you want the 2 pi's, then you should read the detailed article. I will break my promise this one time and say this is why I couldn't resist, but at some point all order will break down. Anyway, this is the way to write the unit operator. So the trick we learned from Feynman is to say e to the minus beta times h is equal to 1 minus beta over h times n raised to the nth power, and then write as many such factors. 1 minus epsilon h and another 1 minus epsilon h. All times that epsilon is this beta over n. So we want the trace of this. But everywhere here, you have to put this unit operator. You got to put that in, and one more thing you'll have to know is that the dot product of a z prime with the z is e to the z bar prime z. That's why this is called an overcomplete basis. If you take 2 of these guys, the dot product is not a delta function. Everybody is dot product with everybody else, and this is the inner product of 2 of them. If you put this completeness relation here, you'll get many such dot products. Then if you collect all these factors, the main thing to notice is, if you take the Hamiltonian here, on the right will be some z, on the left will be some z bar from the next period. And then you can take this operator h, which is a dagger a, and you can replace by z bar z, because a acting to the right will give you z, a dagger acting to the left will give you z bar. So what you will get at the end is that you can write it as a product of many z bars and z's, one for every, what's called every time slice, because we think of this imaginary time. There are n slices, and one for every time slice. You get a factor, and you will get upstairs z bar of some time tau minus d by d tau minus omega 0 z d tau. Now I'm going to, in fact, take the limit, beta going to infinity, for this purpose. Beta going to infinity, if you go back here, beta is 1 over temperature, it's like 0 temperature. If you're going to go to finite temperature, you will have to be a little more careful. I'm just doing 0 temperature problem. Now, how did I get all of this? Of course, if I had enough time, I would tell you all the details, but at least part of it you can understand. The omega 0 z bar z, you get by just this. This is a little more tricky. What you actually get would be a factor that looks like z bar of some t plus epsilon minus z bar of t times z of t. This e to the minus z bar z comes from this factor, and this one, z bar tau plus epsilon z bar tau, comes from this one. That part's actually very legitimate, but what is not correct, or obviously correct, is to replace this by d tau. times epsilon. In other words, we don't know that z bar of tau is epsilon minus z of tau. It's really a small quantity that we can write as a derivative. That's the part that needs a lot of thinking and specification, so I won't go into that either. There's no assurance that when you go from one time slice to the next, the state z bar will be very close to the z bar of the earlier one. But it works, it gives you all the answers you can get by standard operator methods. Okay.
Question?
Yeah.
Is z bar the complex conjugate of z?
In these integrals, you can treat z bar and z as just independent variables. So that if you come to this rule here, you could, if you like, write it as dx and dy, or you can treat z and z bar as independent variables. That's always a big problem. When did z bar become independent of z? Especially when you study conformal field theory, it's done all the time. They are formally independent. But if you come to the physical problem, like this one, when I take the adjoint of this state, then z bar will be x minus iy and z is x plus iy. Okay.
Question?
Yep.
At what stage did I decide to resolve the identity at intermediate slices in very close time?
Yep. You can make it as close as you like. There is still no guarantee.
Why did I decide that? I mean, the way that you expanded the e to the minus beta 8, I didn't see why you resolved it in close space time.
Oh, because Feynman's goal in the end, for example, if you do this in a harmonic oscillator problem and using the states x, for example, you can use that if you like. Then you want to imagine at every time slice there's an x variable, and if you can get them close enough, you want to see a path. And this is viewed as sum over paths. Feynman's goal was to write it as a sum over classical paths. And a classical path is defined in the continuum in time. And the closest thing to that is have a very, very large number of time slices. There are also other advantages, is that if the Hamiltonian has parts that do not commute, once you raise it, once you divide it by this n, you don't have to worry about the non-commuting parts of different terms in the Hamiltonian. It can contain an x term and a p term. You don't worry about all that because the non-commutativity is proportional to the epsilon x times epsilon p, which is epsilon squared. All right. What I want to say now is that I'm going to take, so this course is not really about how to do this. It's only to tell you that there's a problem, either in statistical mechanics or quantum mechanics, that looks like an integral. That's all I want to tell you. And what I will also do is always take the Fourier transform of this variable z of tau into z of omega. Imagine if you've done the Fourier transform, then you will have dz bar omega, dz omega, then e to the z bar omega, I omega minus omega naught, g of omega.
Question.
Yep.
Can you say a few words about the boundary conditions?
Yeah. In this integral, if beta was finite, then you will want periodic boundary conditions. Where is this expansion I wrote? It was here a minute back. Anyway, I wrote something like this. If the I omega tau, z omega. If you're working with finite time, since you're taking a trace, you want z of 0 to be equal to z of beta. That will quantize omega discrete values. That will guarantee the periodicity. When beta goes to infinity, we don't worry about it because all omegas are allowed. That's why this is an integral over omega rather than a sum. Zero temperature.
Sorry, another question. Where is z dependent on tau?
When did z become dependent on tau?
Yeah.
So you remember I put many such factors, right? Starting from the first one. So imagine the interval 0 to beta to be divided into large number of intervals. This is n times epsilon, this is 0, this is epsilon, and 2 epsilon. Every time you put an intermediate state here, you have to write dz bar, dz, like that. Well, you cannot distinguish between the states you put in here and the states you put in here. But these fellows will carry a label of n epsilon, where little n epsilon is the time measured left hand. So every slice has got a label, and z of tau is the continuous label, z of little n times epsilon is a discrete label for the unit operator you put in. Yeah?
So how do we maintain the commutation relations which we had between the operators at equal time? How does it feed into the z and z bar here?
Okay, I just cannot go into that now. What will happen is, if you do it with x and p, you can put the x on. You got to ask yourself, besides the partition function, you want what are called various correlation functions, and you got to put in operators. Then you must relate the average value of Heisenberg operators to what you will do here. Then you will find that whether you do xp or px does make a difference. Okay, so that's something. How commutators are contained in the path integral is tricky, so I don't want to do that either. Yeah, look, I think the only part I wanted to mention here is that quantum mechanical problems have the formula appearance of a path integral. That's really the only point I want to make right now. I think later on, I mean, if the question time, if I have time, or afterwards, I will try to tell you what I know about this. There are parts of it which are still not satisfactory to the mathematicians. Even real Euclidean quantum mechanics has parts that people don't like. And quantum mechanics here, with all these factors of I, is very hard to justify. My practical view has been that you will get all the correlation functions properly here. To get even the partition function with this thing takes a lot of care. If you do the naive partition function, you probably get infinities in the path integral, whereas we know the correct answer is finite. Look, I will be happy to talk about this in the break or afterwards. I have thought about some of these things and I already answered some questions, but I cannot do that now. In this partition function, sometimes one can ask the following question: what is z bar of omega 1, z of omega 2, and which is defined as writing z bar of omega 1, z of omega 2, all this action divided by the partition function. That looks like a statistical average of some variable in the sum over states in the Boltzmann way. So this is called a correlation function. Now, if you do this correlation function, basically what you have to know is how to do a Gaussian integral. And this integral over omega, think of it as a sum, then there's a whole bunch of variables, each with the label omega, and you're trying to do something like z bar z times some number a. dz bar dz. If you can do this integral, you can do anything you want. So you just have to figure out how to do this integral. So if you pretend that these complex z's are like real z's and do the integral, you will guess that the answer is 1 over a. Because this guy, with some number here, will be 1 over a, this will be 1 over a squared, and when you take the ratio, you will get 1 over a. That's the only integral one has to know how to do. That's a Gaussian integral, and the simple answer is the average of z bar z is 1 over whatever is sitting here. Once you do that, you are ready to do this problem, because if you pick z bar of omega 1 and z of omega 2, if the omega 1 and omega 2 do not match, that's like doing an integral of either z or z bar, and that you can show is 0. By the fact that this integral is invariant under phase rotations, and then this is not invariant, we can show it is 0. Therefore, this thing will be 0 unless omega 1 is equal to omega 2, and you get 2 pi delta omega 1 minus omega 2. And if the omega 1 is equal to omega 2, you will just get this point. In fact, if you want, there's 2 pi here. This is the only integral Now sometimes people are interested in a lot of z bars and a lot of z's. I'm not going to write the labels, 1, 2, 3, 4. So I want to put here not 2 of them, but 4 of them. If you put an odd number, you don't have any chance. You're going to get 0. If you put an even number, you can ask what it is. And all of these can be written in terms of this. That's called Wick's theorem. If you call them 1, 2, 3, 4, you will find it's like z bar 1, z4, z bar 2, z3, and a lot of permutations. So the averages that one is always interested in can all reduce to knowing this single average, and this single average actually. Okay, maybe I'll stop for a second. Is there any questions here? Okay, if you know how to find these averages, you can go back to the usual quantum mechanical problem, and you can ask if the Heisenberg operator x at t and x at 0, if you want to trace e to the IHT times this, you can get that quantity in terms of these things. You can do quantum mechanics and statistical mechanics, all based on this integral. Okay, so that is the boson problem. But the problem that I'm going to be interested in is really the problem with fermions. So for Fermi problem, also you have a fermion harmonic oscillator, B dagger B. But this oscillator has weird commutation rules, which is that B with B dagger is 1, and anti-commutator for B with B is the same as anti-commutator B dagger with B dagger, which is 0. This anti-commutator is just B squared plus B squared, which is 0, and that's the Pauli principle that makes sure that the harmonic oscillator cannot be doubly occupied. So this harmonic oscillator, if you solve it using anti-commutation rules, will have only 2 states. You'll have a ground state, you can think of it as no quanta, and a state with 1 quanta. That's it. If you try to use the raising operator twice, you will get 0. You can start here and go up once. If you try to go up twice, this just means B dagger squared is 0. You won't be able to go twice. So this oscillator, if you like, describes a quantum state in which you can either have 0 fermion or 1 fermion. 0 fermion, you can take to have 0 energy, and 1 fermion, you can take to have energy omega naught. So these oscillators have different commutation rules, and then you can ask, what is the trace e to the minus beta h for this problem? The answer to it looks very, very similar to what I wrote for bosons. You will have some new variable size, and the answer looks like psi bar omega I omega minus omega naught psi of omega d omega over 2 pi. Okay, so those who know the dark secrets will tell you that even though this integral looks exactly like this integral, the integration variable psi is not an ordinary number. These are called Grassmann numbers. They are things which don't obey any of the normal rules of ordinary numbers. In particular, the product of 2 Grassmann numbers changes sign when you reverse their order. So if you've never seen them, this sentence will make no sense. And if you've seen them and you've gone through all the details, by now you're in love with them and it's too late to change your mind. So in my case, I figured out how to work with these, and it's quite amazing how one can take this problem and write it formally in this form. But I can tell you that you should draw a black box around this if you don't want to look inside the hood. You will never really have to know how to manipulate these variables to follow my lectures. But of course, if you're one of these people who wants to know everything, then you should go and read my notes where I tell you from the beginning how to deal with this problem and end up writing an integral of this form. Okay. There are even bigger questions on what the hell this means. Okay. But Again, we know that it's a recipe or a calculation tool that gives you all the answers we want for the Fermi oscillator. You can ask for correlation functions of fermionic harmonic oscillator operators at one time and the next time in the ground state or in a thermal state. You'll get all the right answers by doing this integral. Here also, all you will want is what is psi bar omega 1, psi of omega 2. Again, it's defined the same way. Put a psi bar psi here, divide by z. And that answer is also exactly the same. 2 pi delta omega 1 minus omega 2 over I omega 1 minus omega 0. And there's a similar rule on what to do when there's 4 of them. Psi bar, psi, psi. Then also you will have to take products of 2 at a time, but there are extra minus signs coming in, which I don't want to go into. That's connected to the Pauli principle, or if you like, to the fact that psi, every psi anti-commutes with every other psi. There are some minus signs. But all averages of products of even number of operators, everything is reduced to this one thing. That's all you have to know. Then what are the embellishments of this problem? What can you do to make it a little more interesting? Well, you can go back and say, I want many oscillators. If you do that, then you'll come to this step and you'll put some, maybe I'll write here. If you've got an oscillator problem with many, many fermion oscillators, then suppose your Hamiltonian looks like sum over I, bi dagger bi. They could all have different frequencies. Let me take a case where they all have the same frequency. Then it is repeated with an extra label, I agree with. But what's more interesting may be a problem where you have some interaction between them, b dagger I, bi squared. Well, if you do the same trick I told you, then you will get Z, this product. Now let me make a shorthand notation with a square bracket. That means this whole product over omega of all these signs. Then you will have e to the, now you'll have a new index, psi bar I omega minus omega naught, psi bar of omega the omega. Then you will have the following operator. You'll have psi bar of omega 1, you'll have psi bar of omega 2, psi of omega 3, psi of omega 4. Then what should we have? D omega 1 up to d omega 4. Then we need a delta function of omega 1 plus omega 2 minus omega 3 minus omega 4. Then you will have I, let's see, you will have I and J and J. So what we have to remember in our mind is, in this Boltzmann weight, the problem with no interaction between oscillators will look like this one. And if you put interactions, barring some fine points, basically replace every B by a psi, every B bar by a psi bar. You got to be a little careful that all the B's are to the right and all the B daggers are to the left, because we only know that the eigenstates we take are eigenstates of the fermion operator. For example, B acting on psi is psi times B. If B dagger is acting on psi, you don't know what to do, so you must rearrange this so that all the B's are on the right, all the B daggers are on the left. Again, that's a detail that we don't have to know for this course. I'm not going to focus on the real technology of how to do these integrals, but on the main topic for me, it's quite different. All I want you to notice is that in the simple case of n oscillators, Fermi oscillators with this interaction, this is the integral you want to do. Now, can you do this integral? Well, it's not in one of the tabulated integrals I gave you. But what you can do is to take this e raised to all of this, bring it downstairs as a power series. It looked like 1 plus lambda times this plus lambda squared times 8 Fermi fields and so on. Then go back to this rule I gave you here on how to find the averages of any number of Fermi fields, and you'll get a big mess. Well, you ask a stupid question, you get a stupid answer. That's the answer to this problem. It's not easy, but it can all be done in a power series. At the moment, the only way people know to do the integrals is by power series. Bring everything downstairs except for this quadratic form, and then do it term by term, and you get what you call Feynman diagram, or just perturbation theory. All right, so that,
Shankar?
yeah.
Sign error. Just one.
Well, with fermions, you're telling me it's a sign problem?
Yes. It
Okay.
should be e to the minus lambda.
That's correct. Very true. Even in this godless world, there are some rules. Well, I'm not sure, Pierce. I have to think some more, because it might have been e to the minus lambda times psi bar psi, psi bar psi. And if you wrote it as psi bar psi, that could be more.
Oh, that's true. With your I and J, where you've got it, it
Yes.
might be the plus.
Maybe I got it. There's 50% chance I'm
Yeah,
right.
you got it.
We're only arguing over a sign problem. Good chance. Okay, I think by luck I got it
You
right.
got it right with your I and J.
I think the point is, since these are all anti-commuting, the interaction looks like psi bar, and it's certainly true that you're taking e to the minus the Hamiltonian. That's why it's a minus sign. But I'm always used to writing psi bars on the left and psi on the right. And anytime you mix up two of these guys, you get a minus sign. That's why it looks like plus. Okay. So this is to just make the opening statement that many interesting problems look like partition functions. That's it. Some are integrals over ordinary numbers, like z and z bar. Other are integrals over these funny Grassmann numbers. But after a while, you just learn how to do the Grassmann integrals. So then let's ask, what is the process of renormalization? So I'm going to take the world's simplest possible problem involving partition functions. It's got only two variables. Here I really mean only two. This is not shorthand for anything. Take a partition function that involves two variables that looks like this. This is your problem. Then what you will want is some averages. You may want the average of x squared. Then you know what to do. Put an x squared here, do the integral divided by z. I think we all know how to do that. Or a y squared, or an x squared, y squared. We can do all of it. Right? If you want to do average of x squared, y squared, you will do dx, dy, x squared, y squared, e to the minus a, x squared plus y squared divided by z. It's a product of two integrals. You can do both of them. So this is called, we like to call this a free field theory. Just for us, name. Describe degrees of freedom that don't talk to each other. X's don't talk to y. Not only that, the x Boltzmann weight is a Gaussian, and we know how to do Gaussian integrals. This is a problem you can completely solve. And this is called a free field or a Gaussian problem because it involves Gaussian integrals. If this is your problem, you have a very good life because you don't need a renormalization group, you don't need anything, you can write all the answers. But the typical problems of this world look like this. They've got terms that depend on some, let's say I think one more parameter, dx dy e to the minus a times x squared plus y squared minus b times squared. What if this is the problem? Well, you can do what I said earlier, which is to bring this guy down in power sub begin. You can do all the integrals. But let's keep it the way it is. Let's keep the whole thing like that. Now if I ask you how to find the average, so let me write this. I'm tired of writing in this long form. Let me just say it's some energy that depends on x and y and a and b. If you integrate over x and y, the answer will depend only on the parameters a and b, which is why I write the partition function as a function of a and b. This is the problem that's given to you. Now, in this problem, x and y are talking to each other. You cannot factorize the integrals, because when you open up the exponent, it's an x squared, y squared term. So you cannot do one integral at a time. Now let's imagine that for some reason, you are only interested in the variable x, and you have no interest in the variable y. And you want only averages of functions of x. Now I'll come to in a minute to why you find yourself in this situation. So it's a limited question you're asking. X and y are both in the problem, but you are obsessed with x. You want averages of all kinds of functions of x. Let's see what you have to do. You have to do dx, dy, f of x, e to the minus e of x and y and a and b divided by dx, dy, e to the minus e, x and y, a and b. Okay, now I say, let us do all the integrals involving y. That I have dx, f of x, e to the minus b prime of x, a prime and b prime, divided by dx, e to the minus b prime of x, a prime and b prime, where this fellow here, by definition, is this thing integrated over y. In other words, if you do integral dy, e to the minus e of x and y and a and b, I'm going to call that e to the minus e prime of x, a prime and b prime. If you do, after all, you can do the y integral first. Your f of x is not interested in y. You do the integral. This is a sum of positive numbers. The integral will be a positive number. So you can always write any positive number as e to the minus something else, which is real. That something is a definite number. We may not know how to do the integral, but it's some function of the remaining variable x, and we have new parameters, a prime and b prime. So the virtue of this b prime is that for a person who is only interested in functions of x, you don't need to talk about y, but you have to use this Boltzmann weight. This Boltzmann weight, used in the top and bottom, can be used to find average of x, which is identical to the answer you got when you did it, when you formulated the original problem. There's absolutely no loss of information in using this new Boltzmann weight. But this new Boltzmann weight, if you write it out, may look like e to the a prime x squared minus b prime x to the 4th. It might also have other parameters that you did not even put in before, c prime x to the 6th and so on. But this new Boltzmann weight will give you all the numbers as before. I hope you see that. That is the part I want you to follow. Forget the minus signs and 2 pi's. That's not important. This is the most important part of the renormalization program. If you got functions of many variables and a Boltzmann weight that depends on many of them, or let's say 2, and you are interested in a function involving only one of them, you can, in principle, integrate out the y variable entirely and give yourself a new Boltzmann weight, which will reproduce all the numbers with no loss of anything. Yes?
How can you be sure that the Boltzmann weight is always positive? Obviously, here you can. You've got a nice integral with nice x's and y's.
Right.
But later on, when you give us your...
But with fermions, the Boltzmann weight won't even be, forget complex, they won't even be real numbers.
Okay.
They would be Grassmann numbers, which don't even have numerical values. Right? Grassmann variable psi by itself does not even...
Well, let me rephrase it. How can you be sure that the E prime that you'll get in that case represents the physical, properly normalized energy, something that can relate to a low energy theory?
Oh, because I have not done anything wrong in integrating out some of the variables. And I can write the answer as e to the minus anything. The worst thing that can happen is that anything is not real. Maybe that's what you're worried about. But I'm saying it's even worse than that, that anything can even be a Grassmann number. But it is guaranteed that when you then go back and do the x integral, you will get the same answer as before. This says that if an integral is over two variables, or you can do one, and then with what's left, you do the second part, you get guaranteed to get the same answer. Yes?
Just read, because as you do that, you do everything exactly. So you might as well even have done it in real time, it still would be exact. So that addresses that, I think.
Yeah, it is just the fact that in a multiple integral, you are free to do one part of it, then do the rest. But what is interesting is, this is a useful concept if your f depends only on x. That's the main thing. If you happen to be interested only in the statistics of a subset of variables, then you may banish from the problem the variables you're not interested in. But to banish them without thinking, one way to banish them is to say, well, I'm not interested in y, wherever I see a y, I'll put it equal to 0. Well, that's how governments operate. They don't like something, they put it equal to 0. That's not how we want to do our business. This is not the same as putting a y equal to 0 because you're not interested in it. It is taking into account y completely and saying what theory of x would give me all the correlations of x is the original theory in which y was involved with x. So that's what you have to do. But then look what you have in the end. Yes?
So you put the functional form of E changes to E prime.
Yes.
Do you understand why A also changes to A prime something?
Yeah, you will see. Look, if A doesn't change, doesn't matter. I will call it A prime.
Okay.
Now you'll find most of the time A will change, and I'll give you some examples where you can see why A will change. Yes?
So you said you can write it as E prime because if you didn't do anything wrong, you should get a physical answer.
Yes.
But is it possible that after you do that, and later you have to do the perturbation theory? So is it possible that when you lost some information...
That's the point. I have lost absolutely nothing in what I've done so far. This step is not an approximation at all. It's how do you say? You do the y integral completely.
Right.
There's no loss.
What I'm saying, yeah, this formalism that you have no loss, but in practical sense, you have to do perturbation theory at a certain point.
Yeah.
Is it possible that at that point, when you do the perturbation theory, you lost something?
Well, when you do perturbation theory, one is the original problem would be perturbation theory in B. The final one is perturbation theory in B prime. In fact, quite often you will gain by doing something. You will find that by going to few orders in B prime, you are better off than going to the same number of orders in B. Yes?
It seemed like in general, so you had a C prime.
Yeah.
So why do you only write it in terms of A prime and B prime?
No. I started out with good intentions of having the simplest interaction I could put in. But one price you pay when you do this game is that you will get new interactions you did not put in. You will get x to the 6th and x to the 12th and so on. That's correct. So one should be prepared for enlarging the number of parameters. Okay, now here is the punchline. This process by which the original couplings A and B and whatnot turn into A prime and B prime and C prime, that's called renormalization. Renormalization has nothing to do with infinities, even though when I first learned it in my youth, it had a lot to do with infinities and quantum field theories were dealing with infinities. But this theory has no infinities. It's got two variables, and you can crunch it on a computer. It's nothing to do with infinities. It has to do with finding effective theories for variables that you're interested in.
I'm sorry, can I ask?
Yep.
How would I take an infinity if I was naive as back in the 40s?
Yeah.
In this problem.
How will I deal with infinity?
So how would I take an infinity in this problem?
Well, you won't get an infinity with a finite number of integration variables. You can get them if you have an infinite number of integration variables, and there is room for infinities there. In simply summing over an infinite number of finite terms, you can get infinities. No? Maybe I'll come to that later, but what you will find is quantum field theory assigns to every tiny volume in space, however small, infinite number of degrees of freedom. And consequently, when you do any kind of perturbation series, you sum over an infinite number of terms and you get infinity. And then the fathers and mothers of renormalization try to find a way to do that sum, because we know in the end when we measure things we don't get infinite numbers, we get finite numbers. That was a trick for how to get finite numbers from a theory that has infinite number of degrees of freedom. I'm now of the Wilsonian school of thinking, where we understand that renormalization is not a business of infinities. You can bring in renormalization even if there are no infinities. That's a way to understand the problems of field theory in this language. I will be happy to talk to you in the break, or maybe if there is time near the very end, if you remember to ask that question. I can tell you the connection between renormalization as applied to remove infinities and renormalization as applied now in condensed matter, where we know there are no infinities. But you see that renormalization is a process by which you trade the problem that's given to you, problem involving x and y and a and b, for a new problem involving only x with a new set of numbers which in principle you can determine that will reproduce all the same numbers. Okay, so the question we have is, so this is called renormalization. By the way, what people do sometimes, I should mention, suppose you do these integrals and you get this theory. You are told in the end you should take a dx times f of x and you will get the same answer. It is common at this point to change x to a new variable, x prime, so that when you rewrite everything in terms of x prime, this a comes back to the same value that you have. See, a will become a prime, but you want to rescale your x to a new x prime so that this a comes back to the same value. I will tell you why you do that in a minute. Then you must of course remember that the x prime you are working with is related to the x you started with by this faction. For example, if a prime is 2 times a, then x prime would be square root of 2 times x. Now the reason, that means all the square root of 2's will be everywhere. So b may become b double prime and this will become c double prime. But it's common somehow to rescale your variable after this so that the coefficient of the quadratic term is a fixed number, usually half. That is something you don't have to do, but it's commonly done, and I will tell you why you do that. But this is, you guys have to know at this point, what is renormalization. All right, the next thing you should know, just part of the terminology, is that suppose you had not just an x set of y, but 10,000 variables. And x is shorthand for the first 5,000, and the y is shorthand for the next 5,000. Then you eliminate 10,000 variables, the 9999 variable. Every time you eliminate a variable, in the world of A, B, and C, I can only show you 3 of the axes here. You start with some value. Maybe you have no C. You start somewhere here. You eliminate one variable, you may end up here and there and there and there. You keep on moving. In the world of possible, what we call Hamiltonians, the world of possible Boltzmann weights. Every time a variable is eliminated, you move a little bit. And that is called the renormalization flow. Numbers will change. It's very important to realize a special role. So the point is, in this simple example I gave you, you can do only one integral, then you're done. But I'm saying in practice, x and y is shorthand for many, many variables. And every time you eliminate something you don't want, you will have one little movement here. So you should think of a trajectory in the world of parameters in which you start with some point and there's a definite process for moving. This describes a flow in the world of coupling constants. And a person with 10,000 variables will use this set of interactions, and the person with 5,000 variables left will use this set of parameters. And they will get the same answer for the remaining 5,000 variables. You can ask, what is the point of going from here to here? This is what you do. The first part of it is what. Then we'll talk about why and how.
Why can you neglect the higher order terms?
So once you start doing approximations, it's a separate story. At the moment, I'm not doing any approximations. Then everything is the way I described it. First, you have to understand renormalization as a non-perturbative, non-approximate method of understanding in your mind the equivalence of a family of problems. Okay, so this is the part about what is renormalization. Yes, one thing I forgot to mention, sometimes it can happen that if you start with a certain magical value of A and B, you come somewhere, then you get stuck and you don't move anymore. Every such term here corresponds to some Hamiltonian, so I will call this Hamiltonian H star. That's called a fixed point. A fixed point Hamiltonian has the property that you put in the A, B, C, and D and whatnot, and you run this machine, and out comes the same set of numbers. And that's called a fixed point. That's going to play a very important role in what we do. So the flow can actually stop. Okay, so just bear, this is the most important picture to bear in your mind. If you don't understand this, you should stop and ask many questions as you want. Because I have not been very careful with the actual technology of doing these integrals. I've been careless with plus signs, minus signs, and everything. That's not the thing. That's something you can pick up later. You should leave with this one idea in your mind on what is the process of renormalization. Yes?
Are we guaranteed to have at least one fixed point?
No. It all depends on the problem. If the physics is such that something will happen, then you're guaranteed to have a fixed point. Okay, so now I'll come to the second part, which is, so this took longer than I thought, but that's just fine. So our deal is that the questions come during the talk. So the question is, if this is what you do, why do you do this? What's the point?
Question?
Yeah.
You call these things Hamiltonians, but is it so clear that what you'll get will be local in time? Like
Pierce is absolutely right. I call them Hamiltonians. A Hamiltonian, by construction, involves a formulation in which you know the present and you can go to the future in a definite way. It's possible that if you took a quantum mechanical problem that had such a structure to begin with, after you integrate out a lot of variables, what remains may not be equivalent to another Hamiltonian. Yes?
Oh, but if you integrate variables locally, it should remain local.
No, if you integrate high frequency variables, because in the end you only low frequency variables, theory cannot be reduced to something that's instantaneous.
No, but probably if you integrate over frequency, if you integrate over all frequencies, but integrate over finite distance around local.
No, but if you're talking about distance in real space is one thing. But generally in the quantum problem there will be some frequencies. And if the frequency integrals go from minus to plus infinity, there's a good chance it has an interpretation as a local Hamiltonian. You normally cannot read off a Hamiltonian from a Boltzmann weight. I think that's the whole point. It's not easy given a stat-mech Boltzmann weight. You can always go from a Hamiltonian to a path integral, but I'm pretty certain that given an arbitrary path integral, look, take electrodynamics. You've got electrons and photons, and if you integrate out the photons completely, the remaining theory of electrons will have non-local interactions in time. And that cannot possibly be written in terms of a Hamiltonian.
Actually, I think I can talk about an example where you can have the Lagrangian can be guaranteed to be local, but not the Hamiltonian.
Okay, but in general, you may be able to find special examples, but one is, but in general, QED is a good example, where if you eliminate the photons, you'll get theory of electrons, which, according to this rule, will be the correct theory of electrons, but it will no longer be a Hamiltonian theory. That's a theory. It's not enough to know just the present variables. Okay, so I call them Hamiltonian. In the statistical mechanical problem, you can only get some Boltzmann weight. You can call it a classical energy parameterized by new variables A prime and B prime and so on. All right, so now the question is, why do you do this? So I'm going to give you two places where you do this to some advantage. It all started with critical phenomena. So in critical phenomena, you've got some degrees of freedom that's just sitting on some lattice. And there is a field phi. So this is sum over all the lattice points. And let me take some Boltzmann weight, e to the minus k times phi at r, times phi at r plus delta, where delta is one of the neighbors of this point phi. Let me see. Probably look like this. So this is a problem. You can do the integral. You got some physics. And here you may try to find a correlation function, phi of R1, phi of 0, divided by z. And that's called the Green's function. That's a correlation that looks at the fluctuations of one point R to what's happening at another point 0. So these are independent variables fluctuating with this common Boltzmann rate, and you're asking what does the product do? Now, when people study this, for classical statistical systems, they find that for the generic value of k, g of r looks like e to the minus r divided by some length called the correlation length. But at a special value of k, on the critical point, people find the correlation function behaves like a power law. It is common to write the power law in terms of number of space dimensions, b, and this new parameter called eta. So what I'm telling you is this. If you take a set of classical variables on an infinite lattice, and you look at the correlation in the fluctuations of 2 points at a distance r, that falls exponentially. But at a certain point, called a critical point, correlations decay much more slowly like a power law. And let us say you do a lot of work in this particular problem, and you write the answer. Suppose you get 1 over r to the 3.6, and you are in d equal to 4. So d minus 2 is 1. Well, that's a bad example. That's too bad. Let me say I get 1.2. I get 0.5. And you decide how many dimensions you're in. Suppose you're in d equal to 2. That cancels an 8x 0.5 for you. If you got 0.56, then 8x 0.56. So you do a lot of work, and you find this power law, and you need up the power. All right, then somebody comes along and changes the theory and adds some more terms. Some k, let's call it k2, and adds a k4 term. It's a product of 4 different phi's. Maybe a phi there, phi there, phi there, and phi there. It's a different problem. It now depends on these 2 variables. But you fiddle with those 2 variables till you find out some combination of k2 and k4. Again, you get power laws. It's a remarkable fact that even though the numbers k2 and k4 you need to get to the critical point is different, at that critical point, the correlation function falls like a power, but this power, if you like, this number eta, is the same for both these problems. The number in front of this, that's not the same for both these people, but the power is the same. It turns out that's a huge number of Boltzmann weights you can begin with. The minute you arrange them to be at the critical point where it's a correlation is power law, you get the same power. And that's a great mystery. That's called universality. The power seems to depend on the number of dimensions you're in. Say, if it's 2 or 3 or 4, that matters. But beyond that, most of the time, for a huge number of problems, you get the same power. Big mystery is, why do you get the same answer to different questions? I'll give you one simple example. There's something called the Ising model in 2 dimensions, where the variable phi, instead of being a continuous one, can be only a discrete number, plus or minus 1. And you can have, let us say, a k2, which is the product of Ising spins, a nearest label, nearest sites, and a k4 is the product of 4 Ising spins. I claim that if you find when each model becomes critical, you read out the power law, and d equal to 2, these cancel, you get eta equal to 1/4 for both these problems. In fact, an infinite number of problems have the same answer. And you will never learn why they have the same answer just by solving the infinite number of problems and getting the same answer. That doesn't tell you why you got the same answer. Normally, you would think the input to this calculation are these parameters, and the output is this number eta. How can you have a machine where you change the input and the output doesn't change? That's the question you ask. And you don't get that by solving it for many inputs and getting the same answer. And you're just amazed, but you don't understand. Okay, so the renormalization group will tell us now how that can happen. The first thing, by the way, is that all these properties I mentioned are for very large distances. This behavior of the Ising model at the critical point, 1 over r to the 1/4, is not true when r is 1 lattice spacing or 2. If you go very, very far, this is where you find the universal behavior. Alright, so the question is, why do different people get the same answer? Okay, that's what we want to understand. So I will tell you now, in the RG language, why that is possible. You notice that this G of R is the average of phi of R, phi of 0. And if you write every phi of R as some phi of k, e to the ik dot r, sum or integral over k, doesn't matter, then you can see that G of R is G of k, which is a correlation function of 2 phi's times e to the ik r dk. dk is shorthand for in any number of dimensions. I'm just saying, if you go to the Fourier transform variables, we all know from elementary quantum mechanics that if you're interested in very large r, you should go to very small k. So the physics of large r is controlled by the variable phi of k for small k. So it follows that if you come to this partition function and you write here product over phi of k, e to the minus Boltzmann weight that depends on phi of k, and all these other coupling constants, k2, k4, etc., that if you divide this into phi of k's, where k is less than some number lambda and k is bigger than some number lambda, then all the quantities of interest are controlled by phi of k for k less than lambda. And the lambda can be made smaller and smaller and smaller, because in the end, the very, very long distances are controlled by variables at very small k. So this is a concrete example where the x variable is like phi of k for k small, and the y variable is phi of k for k large. You start your problem, I start my problem. We got all the k's in this problem up to some, lattice. The biggest momentum you can have is 1 over lattice space. So we both start with all this momentum. Your system is critical and mine is also critical. And I'm trying to tell you why we can get the same answers for the power law at the critical point. Because what will happen is, we both tell ourselves, I'm not interested in every distance, I'm only interested in correlations at very long distances. Therefore, they are controlled by this phi of k's for very small k. I start integrating out the larger momenta in the problem. And every time I integrate the larger momenta in the problem, I change my coupling constants from, in this problem, let me draw you a picture here. I may have a k1 and a k2 and a k3. I start somewhere and I go like this. Suppose I find I get stuck at some k star. You start somewhere else, and you do this many times, you also get stuck at the same k star, and somebody else starts there, they also get stuck at the same k star. It is clear then, by the time we're coming to the physics of long wavelengths, which is what controls our problem, we're all using the same interaction. And of course, then we will all get the same answer. That requires then that be a fixed point, and that all people whose systems are critical, they can get critical by a variety of ways. One person can use only a K1 interaction, but for a certain value of K1 it will be critical. Other uses a K1 and a K2, then for a combination of K1 and K2, that person is critical. They all look like they're different problems. Indeed, they are different if you ask very detailed questions. If you look at a correlation between neighboring sites, they will get different answers. But that's not what you're asking. You're asking for a very long distance. Then what we do, here's the whole point of the RG. We don't solve the problem we are given. We trade the problem we are given for another one, and then another one, and another one. Each one is guaranteed to have the same answers for the remaining variables. The remaining variables here is phi of k for very, very small k. Then the problem that I exchanged it for in the end can agree with the problem you exchanged it for in the end, and that's why we all get the same answer. That's the role of fixed points and so on in critical phenomena. So the one question was, how do you know you'll get a fixed point? Well, if you have a critical point in your problem, if your system goes through a transition where the correlation changes from exponential to power law, then it's pretty certain that there will be a fixed point in that problem. It's the existence of the fixed point that you can reach, starting from many starting points, that explains universality. So that's one example in StatMech for which you use this. Any questions about this? I mean, what you should know in the StatMech problem is, what is the analog of X? What's the analog of Y? And why did we get rid of Y? And why everyone gets the same answer? Yes?
Experimentally then, how do you know that the quantity that you measure is in a long distance enough sort of property that you actually sort of are applying the long wavelength?
Well, operationally, you can measure these correlation functions, phi of r, phi of 0, by some neutron scattering experiments. Then you can ask how it behaves in R or how it behaves in K. You can do the Fourier transform of that and ask how it behaves in K as K goes to 0. If you get a power law behavior, then you are in business. Then for that power law behavior, the critical theory will tell you how to calculate that power. In a Gaussian theory, the green function phi of k, phi of say minus k will go like 1 over k squared. In interactive theory, it can be any power you like at the critical point, and the challenge is to find the power. And the amazing thing is the power is the same for all Hamiltonians or entities that are critical.
So I guess I'm asking how do you know that you're close enough? So you do this neutron experiment.
Yeah, if you get power laws, you are close enough. If you begin to see a power law. See, normally,
a lot of data though, often looks like a power law, right? Even though you may not be close enough so that you get the true power law. If you don't have a large enough.
Yeah, this is a theory about the true power law. Quite often, it can happen that in the beginning you see one power law, then it can become exponential. That's another thing that can happen. If you take a system not at the critical point, but slightly far from the critical point, then at very short distances or moderate distances, it may look like a power law. Then later on, for example, the function you work with could look like 1 over r to the 1/4 times e to the minus r over 10,000 or 1 million. That for small r, you won't see the exponential, you will think it's power law, but eventually you will see the exponential. That means you are still not critical. And you got to tune your dial a little more till you absolutely and completely kill this term, and that's the theory for which there is universal behavior. Okay, the second, yeah.
Sometimes below the critical point, you do have the power law. For example, in the causes under the causes.
Yeah, that's a weird creature. There are special points where you don't have an isolated critical point, but continuum of critical points. Yes. So I was going to give the second reason why you use renormalization group, which is really the problem that I'm interested in, that I want to talk about. Those problems are the following. I have some Hamiltonian X naught and has some interaction X1. And let's say it's written in terms of some bosonic oscillators, A1, A2, etc., a large number of bosonic oscillators, each with its own frequency, omega 1, omega n. These are low energy oscillators that excite very easily. These are high energy oscillators, very hard to excite them. Then it's clear that if you're in the ground state where every oscillator is in the lowest energy state, the low energy world will involve exciting these low energy oscillators. The big guys won't get very excited. Suppose I'm interested in only very, very low energy physics. I'm not interested in very high energy physics. Then what I may like is, suppose I can solve this problem completely. Suppose this involves non-interacting oscillators. I want to put on the interaction. And I want to ask, does this interaction really make a difference? Is it important or is it not important for this problem? Of course, everything you add is important. If you put a term in Hamiltonian, it's going to change everything. But what I may be asking is, if my states look like this, single particle states look like this, I will want to focus on a world where there are some very, very low energy states I'm interested in, and not in the high energy states. I may want a theory in which the Hilbert space is shrunk in size from everything that's possible to everything that's possible at the lowest energies. Then I may want to trade this Hamiltonian for another Hamiltonian, which lives in a smaller Hilbert space that contains my guys, that doesn't contain the states I'm not interested in. You can ask, in that limited world, is this coupling important or not? It can happen quite often, that even though the coupling looks very impressive in the bigger Hilbert space, when it comes down to really low energy physics, that coupling is unimportant. Operationally, it means you put some number lambda equal to 1, and you solve it on the computer, you compare the lambda equal to 0. You find at very, very low energies, the numbers look the same. It can also happen that you put lambda equal to 0.01 or 0.01, it looks like a very small number. But by the time you come down to the lowest energy states, you're finding that adding the tiny number makes a huge difference to the states at very low energies. In other words, the x in this problem is low energy physics, the y in this problem is high energy physics. You're only interested in very low energies. It is not obvious that a term you added as a perturbation is important or not. You cannot be fooled by the numerical bigness or smallness of this lambda, because its ultimate effect in the world that you're interested in could be different from the superficial effect. So what we do in those problems is the following. We take this h naught and we write a partition function for it that looks like some integration variables times some Boltzmann weight. Then we then we start like this. Now it turns out in the problems that I look at, S naught is actually a fixed point. In other words, if I do the renormalization of eliminating variables, the S naught I begin with will reproduce itself. By the way, one theory that reproduces itself every time is the Gaussian theory. You see that? Suppose you got a lot of variables, x squared plus y squared plus z squared, all of them times the number a. If you eliminate z, it doesn't do anything to x. If you eliminate y, it doesn't do anything to x. So as you eliminate variables in the Gaussian theory, the input numbers are the output numbers. So Gaussian theory is the fine example of a fixed point. So let's take a simple case where the starting Hamiltonian is a quadratic function of the a's, and this integral here is a quadratic function of z and z bar, in which case it's a Gaussian theory and it's a fixed point. Okay, then what we can do is we can add this term now. We're going to add a term to the theory of function of lambda. Looks like d psi. I'll tell you what this means. Times e to the s naught plus lambda times whatever you add. Question is lambda important for me or not? No, the variables are divided into those that describe low energy oscillators and high energy oscillators. What you try to do is to integrate out these high energy oscillators one by one and ask what happens. Well, several things can happen. If you did not have lambda, S naught goes into S naught by choice. Now if you bring in the lambda, every time you eliminate the variables, the new lambda that you get can be bigger than the old lambda, smaller than the old lambda, or equal to the old lambda. If you find that it's growing every time, then you deduce the fact that this is a very important variable for low energy physics, and that's called a relevant variable. If you find it is getting smaller with every iteration with the flow, then you say it's an irrelevant variable. And what that really means is, even though it looks like an interactive theory, in the very low energy regime, you might as well replace it by a non-interacting theory. It will behave like a non-interacting theory. And this last one, this is called irrelevant. The last one is called marginal. That's pretty rare, but once in a while it can happen. But even with a non-Gaussian fixed point, even if you change this lambda back and forth, it remains a fixed point. These are pretty rare in higher dimensional physics. But in the problem I will talk about, it turns out that is what happens. So you should be ready for all the three cases. So the examples are the superconducting coupling between Cooper pairs of opposite momentum, even if you enter it here with a very, very small number, will eventually grow in importance if you come to very low energies. That may be in some other term that looks very impressive, like Coulomb interaction, much, much bigger than the attraction due to phonons. So you might think, hey, this problem is controlled by repulsive forces, not by attractive forces. But by the time you come to very low energies, you will find the repulsive forces have diminished in magnitude. And if that particular lambda has gone down, the lambda due to the Cooper pair attraction has gone up. So in fact, that's what's going to control the low energy movement. So these are the two places we use the renormalization group. One is to understand why different people get different answers. Second is to ask whether some interaction you want to add is important or not for a certain range of low energies. So this happens also in particle physics, where low energy really means low energy. Look, our world today, we know only some number of particles, right? There's a whole number of particles we don't know. And yet we're able to do business because we're using an effective theory. So by force in quantum field theory, we're forced to use an effective field theory where you have some parameters that depend on the x variables that we can probe. Okay, I want to mention one part of technology before I finish, but I got to ask Pierce, do you agree that the questions were in this, or because it's a loose end, I don't want to carry it till next time.
Right. I mean, we've had a lot of questions.
Right.
We continue on.
Yeah.
It's almost the questions
Yeah.
continue.
So I'm going to assume that if you don't
We're
stop
now
me,
at the point where technically, if we don't have more questions, we really ought to turn it into pure discussion.
right?
Maybe you should talk a little bit more.
Yeah, that's correct. I understand exactly what you're saying. I'll take about 3 or 4 minutes to tell you one technical issue because I don't want to leave it hanging. The last question has to do with how. It's pretty simple. I just mentioned, how do you do the renormalization? Here's where many questions that came up earlier are relevant. Suppose I say, just go back to the old problem, dx dy, e to the minus ax squared plus y squared minus b x squared plus y squared. My goal is to get a theory involving only x. That means do the y integral. So we say, all right, so the theory looks like this, dx e to the minus ax squared, I pull out here, and all the things involving y look like e to the minus ay squared, e to the minus b x to the fourth plus y to the fourth plus 2x squared y squared, right? That's the integral you have to do. Now, unfortunately, no one knows how to do this integral because it's not a Gaussian integral. So what can you do? Because you want this fellow, because this is your e to the minus e prime of x and a prime, b prime, etc. So you want to do that integral. So what we normally do is power series. So we bring this thing down and we write this dy and e to the minus ay squared. Then also this bx to the fourth does not have to be inside the integral because it doesn't involve y at all. So I have dx e to the minus ax squared minus bx to the fourth. And the bad guys look like e to the minus b y to the fourth plus 2x squared y squared. This way, if you like, if you are too lazy to do the y integral, you still have some x to the fourth, which is the x to the fourth you began with. And that part you get for free. That's called the tree level calculation. The effective theory for a person who doesn't want to do any further integrals is to say, just ignore y. Just ignore y is the first pass. So I got low energy particles and high energy particles. I'm interested in low energy. I just say, forget about the high energies. Set them equal to 0. What you get is called the tree level.
Isn't that called the government?
That's the government approximation. It's just set equal to 0, these guys. The more careful approximation is to start doing this integral. How are you going to do this integral? Well, there's a rule that if you take e raised to some function of y times some Gaussian integral y squared, you can write it as e raised to the average of f plus 1 over 2 average of f squared minus f average squared and so on. That's a series for doing this integral. So look, it's not a big mystery. It says bring down the power series. Then you are in fine shape because you'll get b y to the fourth, b times x squared, y squared, or any power of y you're not afraid of doing. Once you do it, you have to re-express it as an exponential. Then this is the doing it for you automatically. So the first approximation to the energy that you want to get from doing the integral is just the average of this function. So average of y to the fourth is a constant. We don't care what the constant is. It doesn't involve my variable x. Then I will have here, so what I'm getting is the ax squared I put in, the bx to the fourth from the tree level. Then I will write for you the first approximation will be minus the average of y to the fourth plus 2x squared y squared. So y to the fourth is a number, which in the Boltzmann way makes no difference. This x squared is not a variable in integrating. Average of y squared is some number, maybe 1 over 8. So the whole thing, look what it does. It gives me eta minus ax squared minus bx to the fourth minus 2x squared times the average of y squared. When I say average, is done with this Boltzmann way. So you can see in answer to this question, a will now change to new number because the x squared term I began with is joined by the new x squared term. So if you like a prime is equal to a plus 2 times the average of y squared. And in this simple example, b prime happens to be b if I stop here. But if I now go to the second set of terms here, where I have to take the average of the square of this guy. Can you see that in your head? When you square it, that will be an x to the fourth term. So when you take the average of that, you'll get x to the fourth times a number that will come and join this b and turn b into b prime. Plus, there will be things you didn't bargain for because there are more and more terms here. There are x to the sixth and x to the eighth, and you should collect all of them. That will give you the renormalized coupling constants. And it's never going to be finished because it's a perturbation series, and you stop when you want to stop. But the rule for doing them, this is something I don't want to go into detail. This is the process, but it turns out you can do everything in terms of diagrams. If you had introductory field theory course, then the renormalization for anything will involve, for example, the B-term renormalization will be given by a bunch of diagrams. They all look like Feynman diagrams. The rule for calculating the Feynman diagrams is the following. All the lines on the outside are the variables you're keeping, and the lines on the inside are the variables you're eliminating. So if you're eliminating high momentum states, these external lines will have a momentum in the domain you're keeping. These will be in the range you're eliminating. So draw the same Feynman diagrams, but the variables in the loop are not going from 0 to your cutoff. They're going from the old cutoff to the new cutoff. They're in a region that you're eliminating. That's the only thing to remember. So that's really a technological issue. Depends on what stage of your career you're in. If you're just learning it for the first time, all you have to know is, in principle, given enough time and enough threads, you can do these integrals to any order that you want. In practice, Mr. Feynman has told us to draw these diagrams. For those who know Feynman diagrams, pardon me?
We've got 5 minutes.
Right. For those who know Feynman diagrams, draw the diagrams, keep the loop variables to the variables you're eliminating, the y variable. So this should be all x's, this should be all y's. Okay, I think now I should stop. This is the end of the what, why, and how for argument. But I will answer questions. Yes?
I have a question from the board. So I understand that you can explain criticality through the fixed point.
Yes.
But is the fixed point always critical?
Yes.
You always get overload?
Yes. At a fixed point, you can show that at every fixed point, the correlation length is either 0 or infinity. There are fixed points where the correlation length is 0. There are fixed points where the correlation length is infinity. So the interesting ones correspond to infinite correlation length fixed points. Right? So every fixed point is not critical. Every fixed point is either 0 or infinite correlation length. Basically, you will find the correlation length is the correlation length divided by some number. How can that be? There are two answers. Either they're both zero or they're both infinite. Yep. Yes.
When you expand the function, you get some series.
Yeah.
And the series is converging or not?
We don't know. Just like in field theory, you don't know.
When I calculate the all diagram or all orders, but I do not guarantee it's...
No, I think there's one point worth mentioning. For those of you who have done some quantum field theory in your past, in quantum field theory, individual diagrams diverge, logarithmically or quadratically or whatever. In the renormalization program, individual diagrams will not diverge at all. Because if your old cutoff in momentum was lambda, and you went to lambda over 2, these guys lie between lambda over 2 and lambda. So there is no infrared divergence, there is no ultraviolet divergence. Every diagram is finite. So the flow is in fact, the change of the coupling constant is guaranteed to be finite term by term. But there is no guarantee that a series of infinite terms which is individually finite adds up to a convergent series. That may not happen. In fact, I believe one of the reasons that Fermi liquid theory or whatever doesn't work for high PC materials is that you can do the same talk there, but it may not converge for strong enough values of lambda. That requires estimating convergence of an infinite series. Yes?
How do you check the stability of the fixed point?
Pardon me?
How do you make sure, I don't know if it's a stable fixed point or not?
Well, every fixed point in high dimensions in the world of coupling constants typically will have a topology that looks like this. Anybody who lies on this sheet will flow into the fixed point. Anybody not in the sheet will flow away from the fixed point. And typically, these fixed points have codimension 1 or 2. That means if you live in 96 million dimensional parameters, 2 will be repulsive and the 96 million minus 2 will be attractive. So it looks like it's not so hard to become critical. No matter what way you pick it, you will flow into it. If you miss, you have to miss in a direction that's apart, outside this surface, critical surface. So a fixed point, we can ask the following question: if I slightly off the fixed point, what happens to me under RG? Well, most of the time, if you're off the fixed point, you're forgiven, you come right back. But if you've got a component outside this surface, then you will move. And the way you move is also very interesting. That's part of the study of critical phenomena. I only mentioned what happens at the critical point. But near the critical point also there are lots of universal properties of Green's functions. Again, the fact that you and I get the same behavior is because no matter where we start, we are all moving on this line, and the physics of this line is what we jointly measure. Somebody had a question in the back. Yes?
This classification of the lambda parameter, marginal,
Yeah.
relevant or irrelevant, has anything to do with the symmetries of the problem?
No. This has to do with whether they are important or unimportant for the low energy physics. Yep.
You have a transition where the correlation method does not diverge as in the first order transition. Is this useless or?
Yeah, well, some people have the renormalization approach to the first order transition, but my specialty is in second order phase transitions where the correlation length is infinite, not where it's finite. So this is suited for what are called second order transitions with power law behavior. Yes?
How do you extend all this formulation for dynamical quantities like conductivity and zero conductivity?
Well, if you can write anything as a Green's function, you can write conductivity as a 2-point function, or I don't know what the terminology is, 2 Fermionic function. Then you can apply the RG to that also.
If you go to finite temperature, so you have a bound.
Yeah, if you do finite temperature, that's fine too. You will have to renormalize the temperature variable as you do the RG. Temperature will be like another parameter in the problem. And it certainly applies to, you're not going to find a fixed point at finite temperature, but the temperature itself will renormalize. Yeah, this applies to all, anything you can write as a correlation function, which is why I think it applies to all the problems this school is going to be interested in. Yes?
Not quite all, because
Excuse me, I'm going to be chairman. Deflect your question and give it to a student over here. Yes, definitely.
From a general principle point of view, as we're doing now, what forbids a constant to flow and change sign? Because you classify lambda prime larger than lambda prime smaller than lambda zero.
You mean if lambda is negative?
Yeah, well, what changes for flowing? So lambda prime is smaller than lambda, but then it flows negative and it blows up as minus infinity.
Yeah, by the way, relevant irrelevance are independent of the sign of lambda.
Yeah, but that assumes that it always flows either to zero or to infinity.
No, it can flow to minus infinity. From slightly negative lambda, becoming more and more negative is called relevant.
So what forbids the case that from lambda equal 4 it flows to minus infinity?
Because when it comes to lambda equal to 0, it will reach the Gaussian fixed point. And after that it cannot move.
And you're guaranteed that you can touch that?
Well, it's got only 2 parameters that I'm guaranteed. Otherwise I'm not guaranteed. If you got more couplings and I can avoid the origin, there could be some flow in the world of many couplings that in one of the coordinates is positive to begin with, a negative at the end. Absolutely no reason the sign of any coupling should be preserved under origin. Yes?
Is there any reason that you can start off with an irrelevant coupling and then it could change direction?
Yeah, these flows are, all kinds of flows are possible, including flows that don't have a fixed point, or flows that are going to limit cycle, but they jump between several values and don't make up their mind. So there's no guarantee that you will get a fixed point. I think the whole idea is that if you saw universal behavior and you're wondering how did I get it, this is a mechanism that says if you had a fixed point, that would explain everything. And in all the examples we know, we are able to find those fixed points in some approximate calculation.
What's the physics of the limit cycle?
I don't know enough about limit cycles.
Okay, I think we're going to hold it there.
Okay.
And thank you very much. Shankar, for
Can I say one thing to the class?
Yes.
I don't know how to write in the blackboard. I just cannot do that, and I start with the best intentions, and it's always going to end up like this. But I'm not going to apologize for my writing. That's why I have those notes you should read. I'm more interested in telling you schematically how it goes. So don't think that part's going to get better next time.
We're going to meet again at 11:30 after coffee. Thanks again, Shankar.